Hello, we're gonna talk about 5.4 charging and discharging a capacitor. This is the basic reference. This one is the symbol of capacitance, stores energy by storing charge and discharge energy through the flow of charge. And this one is the resistance. Allow charge or current to flow but dissipate some of the energy flow as waste thermal energy. This is the equation of voltage drop across the capacitor. This one is voltage change rate. It's same or equal with charge over capacitance. How to find capacitance? C equal to Q over V, charge over voltage. And this one is the equation of voltage drop across the resistor. It's same with the previous one, but this one is equal to current multiple with resistance. How to find resistance? R equal to V over I. I is current, V is voltage. So this one is one of the Ohm law. So here another Ohm law. Current flowing through electrical device in everyday life, so it's so important. So we are building our model in terms of the charge Qt, whose first derivative in time is the current. This one current. So from the previous equation, expressing our current model in terms of charge, rewrite Ohm law. This one is equal with R. Change it, just substitute it. So application in daily life. Electric kettle and iron have a lot of resistor in them. Function of resistor is to limit the current flow through them to provide the required amount of heat. The size of resistor used in electric kettle and iron is determined by using Ohm law.
Hi, I'm Noazima, S55747. Next, we're going to talk about 5.4.1, a capacitor discharges. From figure 5.7, we can see a simple electrical circuit with two elements which are a capacitor and resistor. From this figure 5.7, we can know that increment of voltage of C plus increment voltage of resistor equal to 0. From this equation, we can conclude that the sum of voltage drops across the capacitor and the resistor must equal to 0 because there is no voltage in the circuit. We can restore its voltage terms and express it entirely in terms of the charge Q by substitute equation 5.7 and equation 5.20 into equation 5.21. Then a new equation can be written as differentiate of Qt plus 1 over Rc multiply Qt equal to 0. So we can predict that equation 5.22 and equation 5.10 is similar. So equation can be defined as Qt equal to C1 e power of minus t over Rc, where C1 is initial charge that can be known as C1 equal to Q t equal to 0 because the t is equal to infinity. So equation 5.23 is the solution for equation 5.22 and 5.10. For example, a model of capacitor that has 1000 microfarads is with a potential difference of 12 volt across it is discharged through a 500 ohm resistor. Calculate the voltage across the capacitor after 1.5 seconds. From this problem, we can identify the equation 5.23 which can solve this problem. 1000 microfarads is equal to 0.001 farads. C1 equal to 12 volt and T equal to 1.5. Rc is 500 multiplied 0.001. For the voltage across the capacitor after 1.5 seconds is 0.6 volt. From this calculation, we can prove that the bigger the value Rc, the slower the rate at which the capacitor discharged. The value of C can be found from this discharge curve if R is known. From that prediction, we can know that the decay of the charge is inversely proportional to resistance and capacitance. From this graph, the decay of the charge will be slowed down because this case can hold a larger charge that will take time to disappear.
Subtopic 5.4.2, a capacitor is charged. There are two ways to incorporate a voltage source to revise our circuit model. First, we will extend equation 5.21 and we will get equation 5.26. Then, with appropriate constitutive equations and the definitions of the circuit's time constant, we will get equation 5.27. Equation 5.27 is a valid model by applying a classical result of electrical circuit analysis (KVL). From this graph, we can see that the charge increases exponentially from initial given values 0 and the amount of charge does not increase to infinity. External conditions such as voltage applied can influence the behavior of an exponential system to an extent not anticipated by the sign of the constant lambda. For example, large capacitors are used in car audio systems to provide extra strength to amplifiers when it is required. That's all from us. Thank you.